Hi, my name is Kevin, and currently I'm a fifth-year PhD student at the Complex Systems Group, School of Physics, of the University of Sydney. And today I'll be talking about dynamical and computational properties of heavy-tailed deep neural networks. And before I do that, I would like to thank Francesco for inviting me to present some of my work. And I would also like to acknowledge the two co-authors of this project, Asim Wardak and both our advisor, Paul and Gong. The recent achievements of deep learning in many real-life applications have motivated us to comprehend its theoretical dynamics during the training and generalization of complex tasks. And this talk is structured according to the following outline, where we'll use techniques from statistical physics, including random matrix theory, to discuss criticality in the new setting of heavy-tailed deep neural networks from the perspective of dynamical systems theory. And during the presentation, we'll use physics notation. The expectation operator will be applied to all relevant random variables as brackets. And when a subscript is present, the average will be additionally taken over the indices. The letters L and R will be represented as the left and right eigenvectors of the relevant matrix, respectively. And we will use the words Hermitian and symmetrical interchangeably, since we'll be only working with real matrices. But a lot of these results that I'll discuss, they hold true generally for the Hermitian case. Let us start off with a dynamical system of n components that evolves accordingly to a set of nonlinear equations as given, and around a fixed point, which is defined by Fix equals 0. The dynamics can be linearized as in equation 1, and here y is just the deviation of x from its fixed point, and j is the Jacobian matrix evaluated at the fixed point. So under the assumption that the Jacobian matrix is diagonalizable, the squared norm of y can be written as in equation 2. A fixed point is considered to be stable if and only if through all parts of all eigenvalues are negative. And if this is not met, then the system will move away from the fixed point. So this is a very well-known result in, I guess, an undergrad ODEs course. But I would like to bring your attention to this term on the right-hand side because of the matrix J is not necessarily symmetrical. So it involves the correlations between the left and right eigenvectors, which characterizes the transient dynamics of the fixed point. But this is something we won't delve into today. Now let's take a step away from dynamical systems theory and revisit some classical results from random matrix theory. Let us consider a symmetric random matrix A with dimensions n by n. And the diagonal entries are sampled from a centered Gaussian distribution with half variance. And the up and off diagonal entries are drawn from a standard normal distribution without loss of generality. Everything is drawn independently. The joint probability density function of the eigenvalues then takes form of equation 3. So Wigner had actually derived this one on semicircular law in 1957, using it in the Coulomb gas technique, which is now often attributed to Freeman Dyson. Here we also have, essentially, we have a notion of convergence of measure in the weak sense. And keep in mind that this distribution is self-averaging. So the eigenvalues here we take are over just one realization of matrix, but it's just infinite in size. As this result is really been established, we'll use it as an example and demonstrate the crucial steps of the derivation, since they will be later applied to the heavy-tailed case. So there are actually quite a few methods to get this result, such as using the S transformation. But for today, we'll just use the resolving method, where the resolvent of A is defined as in equation 5, and the eigenvalues of A are exactly the poles of the resolvent. And if you bundle these eigenvalues together, they form an empirical spectral distribution. Since the eigenvalues are self-averaging, we don't really need to make the differentiation between the spectral density and the empirical version. So using the residue theorem, some complex analysis, the empirical spectral density can be linked to the conjugate complex derivative of the resolvent trace. And in order to compute the resolvent, we need to utilize this particular lemma by Anderson, Guinet, and Zeytouni. And this lemma allows us to express the diagonal entries of the resolvent as the inverse of a large summation on this right-hand side. And the superscript in brackets corresponds to the resolvent of the adjacency matrix of the same graph with the node I removed. So right here. And from here onwards, we can really use, we don't really have to make the differentiation between a matrix, or in this case, an adjacency matrix, and a graph. So let us resume the previous example and just consider a simpler version of the Wigner surmise, just for simplicity. So we have an ensemble of symmetrical matrices where the upper triangular entries are all drawn from a centered Gaussian distribution with 1/n variance independently. And due to the strong law of large numbers, the diagonal elements in equation 8, so right here, the diagonal elements, they dominate the sum and lead into equation 9 for large n. And based on a result by Tim Rogers in 2008, he showed that any diagonal elements of the resolvent is equivalent in distribution to the resolvent of the graph with the node I removed. So this is actually a non-trivial result. And based on this, computing the resolvent is reduced to solving a quadratic equation and resulting in the semicircular law derived by Wigner. So Genebre was able to further extend this to the non-Hermitian case in 1965, which gives us the circular law, and we'll talk about this in just a few minutes. So now let us resume to the subject of dynamical systems and consider a recurrent neural network model, or a rate-based model studied by many. And this model is, with its leaky term, negative HI, and the scalar gain parameter, captures the dynamic behavior of neurons where the matrix J characterizes the strength of connection between neuron I and neuron J. So again, this is an example of an ODE. And we know that from the previous few slides, the stability of the network around the fixed point can be exactly evaluated by analyzing the Jacobian matrix. So this is given by equation 12. And this representation highlights the importance of examining the product of GJ with a diagonal matrix. So we really just need to examine this right-hand side because the eigenvalues are just shifted by -1, essentially. And classically, equation 12 is divided into 3 cases based on the value of G, ordered, chaotic, and critical respectively. That corresponds to G being less than, larger than, or equal to 1 respectively. And only in the critical regime when the network is really optimized, in the sense that when in the ordered regime, the network stagnates in learning, and the chaotic regime leads to mixing of signals and noise. So a lot of empirical findings have revealed the weights in networks, whether they be biological or artificial, tend to have non-Gaussian distributions, which specifically can be characterized by this power law. The parameter alpha is referred to as the stability parameter and indicates how heavy-tailed the distribution is. And we recover the Gaussian tail as alpha approaches it too. And we will call these distributions with these particular asymptotic tails as the class of stable distributions. And as shown before, the spectral density of non-Hermitian Gaussian matrices have finite support, which is not the case for non-Hermitian heavy-tailed random matrices. And this immediately creates a problem because conventional theory would always categorize the latter system as chaotic, which is not a meaningful conclusion. And just to provide you with some further concrete evidence, in a recent work, in many recent works actually, you can approximate the continuous dynamics of stochastic gradient descent, which is a method of training the network, by this particular stochastic differential equation, SDE, where you have this potential in the direction of the negative gradient of the loss landscape with some sort of noise due to many batches. And for such a stochastic process, it undergoes or time average mean square displacement if you assume B to be some sort of Brownian motion, right, for large T. And in a joint work with my colleague Guangzhong Cheng and both our advisor Pulin Gong, we revealed that the training dynamics of DNNs shows much more complex dynamics compared just to normal diffusion. So it shows usually subdiffusion at the start and then superdiffusion, and then back to subdiffusion towards the end, as revealed in figures A to D. So this actually shows you that the weights or the training dynamics of a deep neural network doesn't really necessarily follow an SDE driven by Brownian motion. So it's highly unlikely that the weights are Gaussian in this case. And in another piece of evidence, we've fitted the weights of pre-trained networks to stable distributions. And these weights from large DNNs trained on very complex images, such as ImageNet, most of them do not really have homogeneous weights or Gaussian weights. Most of these alphas tend to be way below 2. And this really vouches for establishing a general theory for heavy-tailed networks. So let us state the result for non-Hermitian Jacobians by exploiting locally tree-like properties of heavy-tailed Morano matrices based on a work from our group by Asim and Pulin. A cavity approach can be applied to find the spectral density of the Jacobian matrix. The equation is not really in closed form, but does leave doors for computing the asymptotic tails of the spectral density. So in this case, equation 16 and 17, the exact form don't really matter to us for this talk. So most importantly, with the spectral density present and us ignoring the eigenvector correlations, we can define this Jacobian average as in equation 18, which penalizes small and rewards large eigenvalues to a degree determined by the Sibelian strength n. And for the ordered to critical transition line in red, any state below it will have 0 fixed point. And we now use the Jacobian average at the single point of Gaussian criticality as a point of reference. Basically, as well as all the points on the red line. We trace the upper green lines, which have the same Jacobian average for different values of the stability parameter alpha while fixing n. So the values of n corresponding to the green lines from right to left are I think 1, 3, 5, and 1, 11, 21, so on, up to 101. So the area above a single green line characterizes a smaller proportion of eigenvalues away from their region compared to the ordered transition line in red. So now there's a more generalized notion of criticality. When alpha approaches to 2, we recover the conventional criticality as a single point. But once alpha decreases, so once the weights become more heavy-tailed, the single point of criticality opens up to an area with non-zero measure. So in this case, we have a smooth transition from ordered to critical to chaotic. So to really get this result, we need to figure out this Jacobian spectral density. And let us look at an adjacency matrix of a weighted tree, in this case, a symmetrical heavy-tailed random matrix. And the lemma from earlier on restricts the summation to the neighbors of A because we're working with trees now. And AI, superscript of I in brackets, is the adjacency matrix of a forest made up of isolated trees, with the roots being the neighbors of node I. So this gives us equation 19. But the problem is that we don't have equivalence of these two terms in distribution anymore, which is in contrast to the Gaussian case. Now, using a technique, not by us, but by Bordenov, Caputo, and Chaffai in 2011 originally, and further extended by many other researchers. So once you remove a second node from AI, so A superscript brackets I, this allows us to close the recursion. And in the paper, The authors were able to approximate these weighted trees using PWITs, outpost unweighted infinite trees. But intuitively, due to the sparsity, or in particular the character or the structure of the tree graphs, removing the node J from the perspective of node I is no different from removing both J and K. Okay. And so far, we've only really dealt with Hermitian matrices, but this method of bipartization, sometimes also known as the size doubling matrix or hermitization, was really first discovered by Ginebra, which forces a Hermitian matrix by doubling its size. And in this case, like an extra parameter, eta, is introduced. For Hermitian matrices, the eigenvalues are confined to the real line. Hence, to compute the resolvent, one just needs to approach the eigenvalues from the imaginary direction. But for non-Hermitian matrices, they generally have complex eigenvalues, and eta really acts as a third dimension approaching the x1 plane from above. Again, using the same complex analysis technique, you can recover the spectral density of A. So these are really the key steps of derivation of the Jacobian eigenvalue density. And I guess just as like a final step, perhaps, we can really commute the nodes of H yielding the matrix with quaternionic elements, as in 24. And we really have, in this case, a quaternionic notion of the resolvent, which is also known as the generalized Green's function in certain cases. And we can relate the usual resolvent to the quaternionic one in this particular manner. Okay. And yeah, we can again use this the analogy of equation 8 to get this recurrence relationship for the diagonal elements of the quaternionic resolvent, as in equation 26. So furthermore, we can write the diagonal elements of the quaternionic resolvent as in 27. And if we assume that eta is purely imaginary, then we have certain restrictions on A, C, as well as B. So basically on the diagonals as well as the off diagonals. And in particular, the spectral density, the information of that is encoded in the off diagonals of this equation 27. And in the other case, the diagonals encode the information about the eigenvectors. So we can actually explicitly get the inverse participation ratio for the left and right eigenvalues of A using this. And I will discuss the inverse participation ratio just a little later. And now let's look at a non-continuous version of the network, which is in this case one of the simplest types of neural networks, multi-layer perceptrons or fully connected DNNs, with the dynamics given by equation 30 with our input x naught. So in majority of the literature, the weights IJL are drawn IID from a zero mean Gaussian with this particular variance parameterized by sigma W squared. And the biases are drawn from a zero mean Gaussian with variance sigma B squared. And the good thing is that the pre-activation input-output Jacobian has a very similar structure. So in particular, we have the connectivity matrix multiplied by a diagonal matrix with entries as the derivative of the activations. So these layer-wise Jacobians actually share the exact same form of the Jacobians as in the recurrent neural network case, which allows us to adopt this framework. And it shows us that this particular heavy-tailed initialization, based on the previous phase transition diagram, shows better generalization as well as faster training based on this project. So now let us resume to the inverse participation ratio briefly mentioned prior. So it is essentially for any vector, this inverse participation ratio of V evaluated for moment Q is just this for normalized V. So the summation of the entries of this vector to the power of 2Q. So we can define this notion of multifactorial localization over neurons defined by a non-trivial dependence of Q of the fractal dimension appearing in the inverse participation ratio. So once the amount of neurons n approaches to infinity, you can have this relation as in equation 32. And dq equals to 0 and 1 respectively corresponds to the localized and delocalized spatial profiles over the neurons. So in particular, localized, you can look at figure A, where the sites are very different from others, but delocalized means the sites have very similar magnitudes. So this is exactly what, this is also a very interesting dynamic or characteristic that differentiates heavy-tailed and Gaussian networks. So heavy-tailed, you have this heterogeneity, but for Gaussian networks, everything seems to be much more homogeneous. And this is also reflected in dq, the dq versus q curve. So for Gaussian networks represented by the red curve, dq is very flat, which is almost equivalent to 1 for all q. And obviously we have some finite size effects leading to the red curve decreasing slightly, but theoretically in the infinite size of n equals to infinity, then this curve is just really a flat line of dq equals to 1. But in contrast, you can see how for the heavy-tailed networks, this notion of multifractality is very much more emphasized. And these notions of multifractality or eigenvector localization properties are even carried towards, till after training, as you can see in figure F. And you can see for Gaussian networks for different layers, a lot of these eigenvectors tend to be delocalized still. So obviously there's a drop off towards the end because the final the layer only has 10 neurons, causing the drop off. But for heavy-tailed networks, you see this again heterogeneity throughout the throughout depth of the deep neural network. And again, training does not really lead to big changes of the multifractality of these Jacobian eigenvectors. And for image A, B, C, and E to G, these are just for one particular input because you can only compute a single realization of the Jacobian matrix for one input, but we've done this again for multiple inputs. So this is in the sense like macroscopic across different inputs, and you can see the shape still holds very similarly across many inputs. So furthermore, this multifractality also shows up in the principal directions of the activations. So here for the figure on the right, on the left, you can see how heavy-tailed networks tend to maintain the class separability for different inputs, for different values of sigma w. So for ordered, critical, and chaotic, heavy-tailed networks tend to sort of keep this class separability. So we've projected the hidden layers or the activations onto just the top two principal components, where the colors representing different classes of MNIST. But for the Gaussian networks, you can see that in the ordered regime, everything just brings to a point, which is bad for learning, obviously, and only at the critical phase you can really separate these input classes. But once you get to the chaotic regime, the noises and signals start mixing, and you can't really separate these input classes in a very trivial manner. So let us also look at these quantities, ED, the effective dimension, and this really just reveals how many principal components are needed for the networks to explain the variance. And you can see that the effective dimensions for heavy-tailed networks are generally much lower than that of Gaussian networks. So that sort of reveals a more efficient separation mechanism. And the D2, again, is the fractal dimension, dq evaluated at q, which reveals how multifractal the principal directions are. And you can see how, again, the principal directions of heavy-tailed networks are more multifractal or more localized in a sense. And with the same amount of principal components, the heavy-tailed networks can generally explain much more variance. So in a sense, this multifractality is very important. So you can, so let's say for a given eigenvector corresponding to successive layers, which exhibit large modulus than those at the ordered transition line, quantified by the Jacobian average, which we defined earlier. This causes a subset of spatially multifractal directions in the neural space to consistently appear above the critical line, allowing the eigenvectors to experience expansion in those directions while contracting in others, which is a form of symmetry breaking. And this balance between contraction in some directions and expansion in others allow neural networks to prioritize different parts of the input when training on the problem data set. But for Gaussian deep neural networks, the Jacobian eigenvectors are spatially delocalized so that each direction appears equivalent to the network even after quenching, regardless of the problem data. So Gaussian deep neural networks can only contract or non-linearly expand and fold Jacobian eigenvectors in all directions simultaneously without precision, corresponding to the classical ordered and chaotic regimes respectively. So just to wrap things up with some thoughts of future directions, the main contributions of this project involves a theoretical insight for initialization with heavy-tailed pre-trained weights. And I think more importantly, this is a new type of criticality criterion defined based on the layer-wise Jacobian eigenvalues. And we've also discussed the significance of multifractality, which really appears and is unique to heterogeneous networks. And in terms of future directions, it will be very important to extend this to convolutional neural networks since they're the powerhouse for image recognition nowadays. And it would also be nice to incorporate eigenvector correlations in the future because a lot of the networks are not necessarily infinitely deep in a way where we can really neglect the eigenvector correlations. And since we've only defined the theory for random connections, how can we incorporate training once correlations are introduced to the system? And also we have a notion of time during training. So these are some of the selected references, and thank you very much for listening. And again, a big thanks to the organizers of the Complexity Conclave, including Francesco, Michael, Cristiano, Luis, Pedro. And again, I would like to acknowledge the guidance of my advisor, Pulong Gong, and the assistance of my colleague, Asim Wardak. And feel free to reach out to me if you have any further questions. Thank you very much.